All right. I think folks are done trickling in. Okay. So, good afternoon, everyone. We're going to hear today from Dr. Adeene Denton. Dr. Denton is a planetary scientist and a NASA postdoctoral research fellow at Southwest Research Institute in Boulder, and also an adjunct lecturer at UC Boulder. Until recently, she was a postdoctoral researcher here at LPL, working with Dr. Eric Asfog on the formation of the Kuiper Belt. She earned a PhD from Purdue University in 2022, where her dissertation explored Pluto's internal evolution through the formation of the Sputnik Planitia. And before that, she completed her master's at Brown University and earned a dual degrees in earth science and history at Rice. Adeene's research focuses on how giant impacts shape the solar system, from icy ocean worlds to dwarf planets like Pluto and beyond. And her 2025 Nature Astronomy paper, Capture of an Ancient Charon around Pluto, introduced this very compelling kiss and capture mechanism that's provided a lot of new insight into Pluto and Charon's origin, and that was widely covered in the media. So we're really excited to have her back with us today. Please join me in welcoming Dr. Adeene Denton.
Thank you so much for the introduction, and thank you for having me back. I love Tucson, and I really enjoyed my time at LPL. If you overlapped with me and you did not see me, that's because I worked in Drake, so I was not over here very much, but it's very exciting to be back. And yes, I'm going to talk about the paper that we published in January of this year, which is called Kiss and Capture Preserves an Ancient Charon Around Pluto. And that paper revisits the idea of collisional capture of Charon by Pluto. So the first thing I'm going to do is talk about why we think that happens at all. And also, if my sound goes wonky at all, please just let me know. But this is Pluto and Charon. And the main reason that we think Charon is a captured satellite rather than formed in situ is two main points of evidence. The first is that Charon is very large relative to Pluto, and also that the system has an unusually large amount of angular momentum. So how do you end up with an unusually large satellite with a system that has an unusually large amount of angular momentum? The easiest way to do that would be through a giant impact, similar to how the Earth got its moon. This theory for the capture of Charon around Pluto has been around for quite some time. This isn't really new. It's been around for several decades now. But why should we actually revisit the Pluto-Charon collision? Well, this is because even though the hypothesis has been around for quite some time, our technologies for studying collisional capture have evolved quite a bit. Now, the moon-forming impact forms the foundation for our understanding of satellite capture. When we think about collisional capture of a moon, we tend to think about our moon because it's the system that we know the most about. But analysis over the last 5 years, particularly of giant impact simulations, has shown that satellite capture may operate differently across the solar system. So when we scale from the Earth-Moon system to the Pluto-Charon system, which is farther away in the Kuiper Belt and also a lot less massive, things might work differently. Now, though some of you may not be as familiar with the Earth-Moon collision, so I thought I would show one of the famous videos. This is by Jacob Kegares. This is one example of the Earth-Moon forming collision, where a Mars-sized body called Theia collides with the Earth. And in this case, both bodies lack material strength. They behave like fluids. There's theoretically a lot of melting and vaporization. The large inner body is the moon. And then eventually the large inner body is the Earth. And then eventually the second body is going to become the moon. This is the best video that you will see because I can't do this with my videos. So when you watch all of my videos that I showed you, please imagine that they are as good as this one. Thank you. Yeah, so eventually you'll get the moon out of this and the system is going to stabilize. So this is the framework that a lot of people have for when we think about capturing a large mass fraction satellite around a planet. And like I just mentioned, in the Earth-Moon collision, we can assume that both the Earth and the Moon will behave like fluids because this collision is so intense. Both bodies are relatively massive, so they will collide at speeds that can ensure widespread melting and vaporization. So because of that, we can approximate both of them as fluids and consider that to be fairly robust. Though I will say that people are currently revisiting whether you can actually do that at these scales. But up to the present day, most people have been simulating the Earth and the Moon colliding as if they are two fluids hitting each other and then deforming like fluids. And I'm bringing this up because I'm going to revisit the idea of whether we can simulate bodies as fluids in this talk. And the reason for that is because Pluto is small. Pluto is about 17% the mass of the Moon. And at that size, previous impact simulations have shown that strength is important to impact outcomes. But the effects of strength are complicated. And when I say strength, what I mean is material strength. So strength is the idea that if you are not a fluid, if you are a solid body like a rock or an ice shell of an icy satellite or a Kuiper belt object, you have some amount of intrinsic material strength that allows you to resist deformation up to a point. This is the main concept of material strength. And in giant impact simulations, when we implement material strength, what we find is that it changes impact outcomes. But we're still trying to understand at what scales that's important and also what it does. And the reason why this is of use, not just to the Pluto system, but other places, is because many of the largest Kuiper belt objects have a large mass fraction satellite. It's not just Pluto and Charon. There's also Orcus and Vanth, Eris and Dysnomia, Quaoar and Weywot, and the other ones on this slide. So if we can understand how the Earth-Moon capturing process is different from the Pluto and Charon process, we might be able to understand something that's operating across the entire Kuiper belt, potentially. And the reason why we might want to use Pluto and Charon for this is because we have the most information. On the previous slide, I showed you images from the Hubble Space Telescope, and here's the Hubble Space Telescope image of Pluto and Charon. But unlike many of the other large Kuiper belt objects, we visited Pluto and Charon with New Horizons. So now we have a much more improved understanding of both their surfaces and also how that might connect to their interior structure. So because we have an understanding of Pluto and Charon's geology, we can use that to try to work backwards. So when we're trying to understand Pluto and Charon's origins, as I'm trying to do here in this project, we can begin with our improved understanding of the thermal and structural state of Pluto and Charon today, which we can somewhat understand from New Horizons, and then work backwards. So we have the most information about Pluto and Charon, which makes it a good place to start. Now, before I get into what I've done for this work, I understand that not all of us may be as Pluto and Charon enthusiasts as myself, so I'm going to review a little bit about what we did learn from New Horizons that informed the work that I did. So we're going to begin with talking a little bit about what we think is inside Pluto. I'm going to raise a lot of questions here, and I won't be able to answer all of them, but this is kind of a first look at what we think is going on inside Pluto. So this is a cross-section of Pluto simplified. And I'm going to start from the bottom of this cross-section and work my way up to the top. So the main thing to know about Pluto's core is that it has one, we think, and that the size of Pluto's core is probably around 2/3 of Pluto. So it's maybe 75%. 75% is 60, 75%. It depends on the composition of the rock, which we don't know. So you could say that Pluto is around 75% rock, could be more, could be less, depending on what rock it is. But this is our average estimated radius. And then what is the composition of the rock? This is something that's difficult to understand. Depends on your thermal evolution of Pluto, which you have to make some assumptions at the start and go from there. Hydrothermal alteration of Pluto's core has been suggested because Pluto has, if Pluto's core, which is assumed to be rocky, has radioactive isotopes in it, it does generate heat. If Pluto's rocky core interacts with a liquid water ocean, it could produce hydrothermal alteration, and you could serpentinize Pluto's core or something like that. But none of that's been directly detected, and the timing of how that might work and how warm Pluto has to be for that to happen is all pretty unclear. So what we know about Pluto's core is it's large and it's rocky. And again, the reason we don't know more is because New Horizons is a flyby mission. So we flew by, and everything that we do when it comes to making inferences about the interior, we must do based on what we're seeing on the surface for the most part. So moving up to a fun question, which is, did Pluto have a subsurface ocean, and does it have one today? Well, the answer is maybe. There are several lines of geologic evidence that suggest that a subsurface ocean on Pluto could be likely. And the first of those is extensional tectonics that have been at least partially mapped in this image. This was a paper that James Keene and some other people did back in 2016, which mapped these extensional features that I'm showing you here in orange, green, and yellow. And these structures are interpreted to be, at least in part, from an ocean freezing. So the idea here is that if Pluto has an ocean in the past and is slowly cooling through time, then as the ocean freezes, the entire ice shell expands, and you produce extensional fractures on the surface. So mapping extensional tectonics on the surface of Pluto is an indicator that Pluto at least had an ocean at some point in time. And then the location of Sputnik Planitia today is an argument that Pluto still has an ocean today. I'm not going to get into this as part of this talk, but I'm happy to discuss it later. The main argument here is that Sputnik Planitia, which is that circle, the bright white that is Pluto's heart, is thought to be a massive impact basin. But it is an impact basin that is located close to the Pluto-Charon tidal axis, which is that red arrow. And that's a little unusual because an impact basin should be a mass negative. You're effectively making a hole in the ground. You're removing mass and putting it elsewhere. So if it is in fact a mass negative, then a basin this large should go to Pluto's pole. But instead, it is close to the tidal axis, which indicates that it might be a mass positive rather than a mass negative. And one way that you could have excess mass in Sputnik Planitia is, in addition to the nitrogen ice filling the basin today, which is the white of Pluto's heart, you also have uplifted ocean underneath the basin floor. And because ocean is more dense than ice, you can then create that positive mass anomaly. So together, these suggest that Pluto had an ocean in the past that is slowly freezing to create these extensional tectonics, but that it may still have some component of an ocean in the present to keep Sputnik Planitia where it's currently located. For our purposes, what we need to remember is that Pluto may have an ocean, and that ocean may be geologically expansive in terms of its lifetime, or it may not. Now, I'm getting further up, closer to the surface, and I'm still giving you more questions than answers because the structure of Pluto's ice shell is still largely unknown. And again, the reason for this is because we don't really have geophysical or geodetic information about Pluto. But I can tell you what we do know, which is that we're pretty sure that Pluto's ice shell is almost entirely water ice with a thin veneer of volatile ices, and those volatile ices being stuff like carbon monoxide, nitrogen ice, which is what's filling Pluto's heart today, and ammonia, volatile ices. So the vast majority of Pluto's ice shell should be water ice. The question is, of course, is it relatively cold and stiff to sustain the topography that we observe on the surface, or is it much warmer? And also, how thick is it? And how warm is it? These are things that we can't really constrain because we were getting a snapshot of Pluto at one point in time and having to extrapolate back through time to see, again, how thick it is based on whether or not it has an ocean underneath its surface, or also how warm it is based on the initial thermal budget that Pluto forms with at the start. That's the Pluto crash course. Now, let's recap the major unknowns in Pluto's interior. The first is whether there's an ocean and how thick it is. The second is how active is the core? How do you induce activity in the core that produces hydrothermal alteration in a Kuiper belt object? And then what is the thermal structure of the ice shell? How hot is Pluto, and how does that affect the actual ice shell through time? The cool thing about this is that all of these relate to the initial formation of Pluto and Charon, which means these are things that we can think about when we're trying to reconstruct the initial formation of the system. Now you may be thinking, what about Charon? Well, we'll get to that too. This is a cross-section of Charon, and there's a lot more unknowns here, so I'll be brief, but we think that Charon might be 50% rock, 50% ice. It is less dense than Pluto. And again, these numbers, 50% rock, 50% ice, these come from estimates of Charon's density and the assumption that Charon is differentiated. So if Charon's differentiated, then It's probably close to 50% rock, 50% ice, but there's some wiggle room in here. One of the major questions is, did Charon have an ocean at all? Charon is smaller than Pluto and much less massive, so it's a much more open question if it had an ocean at all. And the reason this is brought up is because some people have suggested that features on Charon's surface are cryovolcanic related, which you need an ocean to do. So we're not sure about that one. And the big one is, how destructive was the initial Pluto-Charon impact that captured Charon? Does Charon lose a bunch of material? Was Charon completely different prior to the impact, and then the body that we're seeing now is the result of the impact or not? Because giant impacts can drastically change the interiors of planetary bodies. So we don't know if what we see today for Charon is a massive change from how it initially was prior to the collision or not. I bring all this up because the outcomes of giant impacts, including whether Charon gets captured as a satellite and what happens to it after that point, reflect both the composition and the internal structure of both bodies prior to the collision. So what Pluto and Charon are like prior to impact will influence what happens during and after the impact. And the cool thing about this is that we can use giant impacts to inform our understanding of both thermal and mechanical variations in Pluto's interior. This is my argument for this is a tool that we can use to try to answer some of these questions. Now, I got to get back to the modeling. Previous simulations have looked at the Pluto-Charon question, have tried to form Pluto and Charon. And the answer is you can do it. You can form the Pluto-Charon system from a giant impact. And these are some of the simulations that were done by Robin Knapp in 2011. She did her initial simulations back in 2005 and then revisited them in 2011 ahead of the New Horizons arrival at Pluto. And this is a snapshot of those simulations. And when I say they neglect strength, what I mean is, again, like with the Earth-Moon system before, these simulations assume that Pluto and Charon can be approximated as fluids. And in this scenario, what you can observe is, so this, I should say, this larger body is Pluto, this smaller body is Charon. And what you can observe if we look at this time series is that the angular momentum exchange that occurs during impact occurs primarily between the distorted figure of the target body, which is here Pluto, and this condensed region of impactor material, such that the impactor, which is Proto-Charon, undergoes massive shearing. And I will just highlight this here. And this is a primary characteristic of these models, right? So the way that Charon is captured by Pluto is influenced by how both bodies exchange angular momentum during this collision. So a large Charon hits Pluto, experiences massive deformation, loses a bunch of its mass to debris, and is eventually captured as a satellite. The main requirements that Robin found are necessary for Charon to be captured are, one, that Charon has to be relatively large in mass. The reason why Charon has to be so big is because, as you'll notice, mostly here is a good example, it loses a lot of its mass to debris. So the final Charon here is a lot smaller than the initial Charon that you start with because it produces a massive debris disk, and then theoretically you get the other moons out of that debris disk. But the other thing that's notable here is an oblique impact is necessary. So Pluto and Charon cannot collide at close to 45 degrees. Instead, Charon enters at a relatively oblique angle. So if 0 degrees is vertical, 70 degrees or so. So relatively oblique. So consider it more of a grazing impact. Charon grazes Pluto, and in doing so, it grazes Pluto just enough to start this process and get captured in a centric orbit around Pluto after losing a bunch of its mass to debris. So the problem with this, and this is all very good, by the way, I'm saying that the problem, as we've learned more, is, as I brought up earlier, at the size of Pluto and Charon, what we've found is strength influences impact outcomes. So then the question becomes, how does strength affect this system? And to better make my point, what I'm going to do is show you a video of what happens for a Pluto and Charon-like body of those same parameters, neglecting strength. The only thing I've changed from what I just showed you is that instead of a grazing impact, this is an impact that's going to be at 45 degrees. The reason I'm going to show you an impact at 45 degrees, Yeah, my impact parameters are down at the bottom of the screen, but you may not be able to see them. The reason I'm showing you impacts at 45 degrees is because 45 degrees is thought to be the nominal impact angle at which things collide in the solar system. So if Pluto and Charon collide and it's not a grazing impact, this is why it doesn't work. They collide and then they merge. And there's all the debris that's getting kicked off. Really big one just went off to the right. But the main thing to note here is they can't retain their structural integrity. Pluto and Charon pretty much immediately merge. This is why you need an oblique impact, because if it's a shallower angle, they just immediately merge with each other. Now, the key question that I brought up earlier, this is what we wanted to look at. How does including material strength change whether Pluto retains a satellite after a giant collision? This is a pretty niche question, but hopefully what I will show you today is that it has some pretty big impacts. And now I have to show you my methods. So this is how these specific impact models work. What I'm showing you here on the left is a diagram of what's going on in pretty much every simulation. So I begin from previous assumptions and then I incorporate material strength. And what I mean by that is I built a system that is nearly identical to those initial simulations that I showed you previously. What I mean is I started with what Robin Knupp did in 2005 and 2011, where I assume that both Pluto and Charon can be approximated with constant interior structures. I didn't change these. So I assume here's Pluto, here's Charon. And two things of note here. Both bodies are assumed to be 85% rock, 15% ice. And the mass of Charon is assumed to be 1/3 the total mass of the system. This is the initial framework that Robin Knupp used. So to see how material strength changes that, I'm starting with those same initial parameters. And here in this image, the sand-like color corresponds to the dunite core, and the light blue corresponds to the ice shell. I tested a range of impact angles and velocities from relatively nominal impact angles, so from 40 to 60, we would consider potentially nominal, anything that's clustering around 45 degrees, as well as more oblique impact angles similar to what was used previously. And then I also explored a range of impact velocities. And in the code that I'm using, we use impact velocities normalized to the escape velocity of the system. And I use between 1 to 1.3. This will mean nothing to almost all of you. But what this actually means is the impact velocity of these two bodies as they collide is roughly around 1 kilometer per second, which could seem fast to you. It is not. Fighter jets fly faster than that. This is not fast. They're colliding relatively slowly because they're not very massive. The other thing I forgot to say is that I'm using a smooth particle hydrodynamics code. This is SPH. So all of these bodies are simulated as collections of particles. I've also used ISO, and I'm happy to talk about how the impact models work, but please feel free to ask me about that if you are curious. Suffice to say that I'm using SPH for this. They are 3D simulations. Now, let me talk about the new things that we're doing here relative to the old simulations. The first is that we are varying spin on the target. So in these simulations, as this arrow indicates, Pluto is spinning prior to impact. We test no spin, so if Pluto is just stationary and not doing anything, and we then slowly increase the spin from a period of 10 hours up to a period of 3 hours, which would be relatively rapid, but also potentially common and feasible in the Kuiper belt. And Pluto's spin is prograde relative to the impact. The other thing that we're doing is implementing strength. This is the big one. So our strength model implements friction, plastic deformation, and thermal yielding, and is similar to the strength model used in the ICL shock physics code, which some of you may be slightly more familiar with, or not. What we find from these tests, and I ran quite a few simulations on the University of Arizona's high performance computing cluster, is that simulating Pluto and Charon as bodies with material strength does produce a satellite. So it does still work. We still get Charon out of this. But we find that implementing internal strength produces this new satellite capture regime that we're calling the kiss and capture because of how it works. And we're calling this a new satellite capture regime not just to get cool headlines in the newspapers, but because this is relatively different from how satellite capture happened before. So what I'm going to do is show you a video of how kiss and capture operates, and then I'm going to talk about it. So to understand this video, the impact parameters are here on the left. So Pluto and Charon are going to collide at around 45 degrees. This is a relatively slow collision, and Pluto is spinning relatively rapidly, so don't forget about that. This is Pluto. So material in this video is colored according to composition and body of origin, which means here's Pluto. Pluto's ice shell is in yellow and its core is in blue. Charon is going to enter from the top right to collide with Pluto at 45 degrees. Charon's ice shell is going to be in green, and its core is going to be in purple. And I have no idea if this will work. Hope my video works. Okay, now that we've all had a little fun. Yeah, so we're calling it kiss and capture because it's very romantic. But we're calling it kiss and capture because the two bodies partially merge and then separate. So I'm going to show this video again without the funny music and talk a little bit about what's going on. So here comes Charon from the right. The two bodies partially merge. So here they are merged together, co-rotating as a single body. You may have seen Charon lost some mass off the back. That's fine. And then Charon slowly starts to separate. Pluto is able to push Charon back off because it's rotating so fast. And they establish this stable system where Charon is independent of Pluto. And as you'll see later, slowly migrating outward. This is very different from how the system worked previously because of several things, which I'm going to get to in sequence. But first, I'm going to step through what's happening in a little bit more detail. So the changes that produce this new way to capture Charon happen almost immediately and are, again, pretty much entirely because of material strength. So what you'll notice immediately during the collision is that Charon partially penetrates into Pluto. So again, here's Pluto, here's Charon. As they collide, Charon is able to push its way into Pluto somewhat, but unlike the previous scenario that I showed you in which they merged together to form one super egg-shaped body when there was no strength, now that there's strength, Pluto is able to resist deformation. So instead of merging together, both bodies maintain their structural integrity. What happens next is they then co-rotate as a single body, a massive contact binary, so kind of like a super Aircraft. During this process, several things are happening. The first is that you will notice is Charon is losing some material out the back. Most of this material remains bound to the system and forms a large debris disk that is outside the scope of these images that I'm showing you, but it's still out there. It's not gone forever. Most of it is still in the system. And then because the center of mass of Charon lies outside of the co-rotation radius, and because Pluto is spinning so fast, Pluto is able to torque Charon, and eventually both bodies separate. It's not a stable merger. So Pluto is able to push Charon back off, and it slowly starts to separate after about 20 hours. So this period here, which lasts from 0 to 20 hours, is what we call the kiss, where the two bodies are partially merged. And then the capture is when Charon slowly starts to migrate outward after this point. Some other things worth noting here are that Charon largely remains the same size, and so does Pluto. They exchange some mass with each other. You'll note that, one, Charon loses some mass off the back, but two, that Charon deposits some of its mass onto Pluto, loses some of its core, loses some of its ice shell. Both bodies are completely resurfaced during this process, but at the end of it, the Pluto and Charon that you have after collision are largely the Pluto and Charon that you had at the start. Charon loses a very small fraction of its mass to Pluto. Pluto loses an even smaller fraction of its mass overall. And both bodies retain the signature of their initial conditions prior to impact. This is what I mean when I say we're capturing an ancient Charon around Pluto. It's because you're no longer losing so much of Charon's mass that it's an unrecognizable body from when you started. Here, we can clearly recognize the Charon from the start at the end. Now, I also want to talk a little bit about how this works in the orbital dynamics of space. So what I'm showing you here in this top panel is the evolution of the collision through time. So from the start of the collision, which is at 0 to 60 hours, which is when we cut the simulation off. And I'm showing 3 things in sequence. The first is the semi-major axis in red, Charon's semi-major axis, its periapsis in cyan, and then the co-rotation radius of the system in gold. I was almost about to say yellow, but it's kind of gold. At any rate, what you'll notice here is that between 0 to around 15 hours, which is when separation starts, things are a little chaotic because this is the initial merger. And then after separation occurs, which takes about 10 hours, then the newly separated satellite stabilizes its orbit. And this orbit stabilization happens relatively rapidly, which is why I can model it in an SPH simulation, because this happens over a period of hours. This is pretty fast. That satellite then stabilizes into this tight, low eccentricity orbit that slowly starts to expand. And Charon is also really close to Pluto during this point. I will note that it is between 2 to 3 Pluto radii away from Pluto. But that orbit is slowly going to expand, and Charon will move outwards. And the duration of that expansion is something that I can't capture in my SPH simulations. And when I say low eccentricity orbit, this is a direct plot of eccentricity here in blue. And you'll see that during the merger, this isn't really relevant, but after the separation, which occurs around 15 to 20 hours, then Charon stabilizes into an orbit that is relatively low eccentricity. So it oscillates between 0.1 to 0.15. And you might be thinking, that's still really high eccentricity. Yes, but it's relatively low eccentricity compared to previous simulations, which found that Charon's orbit was much more elliptical than this. This is what we consider relatively circular by comparison. So this is the orbital stabilization that I'm talking about here. And these peaks and valleys correspond to the fact that because Charon is so close to Pluto, the tidal dynamics are very unusual. And so Charon is oscillating as it orbits Pluto. The last thing I'll say about all of this is the angular momentum. Why do I bring up angular momentum? Because I brought it up at the start. One of the reasons we think Pluto and Charon formed from a giant impact is because of the large angular momentum of the system. So the best way to check to see if we actually did successfully reproduce the angular momentum of Pluto and Charon is to normalize the angular momentum of the system at the end of our models to the angular momentum of Pluto and Charon today. And this is what we've done here. So that top line in cyan is the total angular momentum of the system. The components of the angular momentum of the system are 3. The first is the spin of Pluto. The second is the spin of Charon. And then the third is the angular momentum contained in Charon's orbit around Pluto. So if we sum all of these together, we get the cyan line at the top. And what you'll see is after Charon separates from Pluto and loses some of its mass to debris, we end up with a total angular momentum that is close to the angular momentum of Pluto and Charon today. We did it. Thank you. Thank you for the applause. And my talk is over. No, I'm joking. I have more to say about this because you've given me the time to do so. One thing that I will say is I've just showed you one example here, but the cool thing that we found is once we went looking for, is this just a fluke process that happened one time and happens to be really cool and really fun to set to music? Well, no, it's not a fluke. We found that we can reproduce kiss and capture around 14 times for a variety of impact angles and impact velocities and also sizes. I'll get to sizes in a little bit, but first I want to talk about my pet theory that I really like, which is bringing this back to the geologic evolution of Pluto and Charon, which is why I gave you all that Pluto and Charon information, because Pluto and Charon also has implications, kiss and capture, also has implications for Pluto and Charon's thermal evolution, both before and after the collision. There's basically 2 options that have been suggested for Pluto's early interior. So this is 2 ideas for how Pluto formed that inform how we think it looks today. So these are 2 thermal models where we're tracking 0 being the start of Pluto, 4.5 being present day. And I find these somewhat impenetrable, but the summary is that either Pluto starts cold or it starts hot. And if Pluto starts cold, it forms relatively late in solar system history. So several tens of millions, up to tens of millions of years after the solar system formed. If Pluto forms relatively late, then it starts relatively cold. This black line here corresponds to the base of the ocean, which means at 0 in a cold start case, you have no ocean. Pluto starts cold, and then radioactive decay of isotopes in Pluto's core causes the ocean to slowly form over time. And you sustain a relatively thin ocean today, but this is the cold case because you slowly build up this ocean over time. The problem with this is that if this is the case, and Pluto starts frozen, then theoretically you should have compressional tectonics rather than extensional tectonics, which is what we see. The other problem with this is that it is potentially easier for Pluto to form late and frozen because then you don't need to form it relatively quickly. The reason why I bring that up is because the other option is that Pluto starts hot. If Pluto starts hot, then it has to form early. How do you get more heat into Pluto than just the heat that you can get from radioactive decay of isotopes in Pluto's rocky core? Easy. Aluminum-26 and other quick decaying isotopes early in the solar system. It's just that easy. You put those into Pluto as well, and then you're all ocean at the start, and then you slowly cool off over time. So you start with a thick ocean, and it stays for the entire duration of Pluto's history. I bring this up because if this is the case, then you've really just got to form Pluto extremely quickly. There is currently no consensus over which of these is correct because it's very difficult to say. What we know based on what I showed you is that today Pluto has extensional tectonics and may or may not have an ocean. If that's the case, then maybe Pluto did form hot, but then it has to form relatively rapidly within the formation of the early solar system, which places unusual constraints on Pluto's formation relative to the formation of the Kuiper Belt and many other problems. I bring all this up because I have a solution, and it's kiss and capture. Okay, let me tell you how. So I looked into this because I care about the geology of Pluto and how the geology of Pluto relates to this initial collision. What I found is that a hot start or a cold start for Pluto influences whether kiss and capture occurs. And after this slide finishes, you may think I'm a fraud, but I believe in what I'm about to show you. So what I found is that if Pluto starts cold, kiss and capture works. So in this case, the basal temperature of Pluto's ice shell is around 200 Kelvin. And that either may be cold to you or it may not. But 200 Kelvin at the base of Pluto's ice shell means it's entirely frozen because the melting point of water is 273 Kelvin. So if Pluto's ice shell is cold, you can get kiss and capture. Why? Because the ice shell is relatively cold and thus resists deformation. The strength of ice is temperature dependent. So watch this. As we slowly warm up Pluto's ice shell, it still works. You'll notice that you're getting more debris. There's a little bit more mass exchange between both bodies. This is because the ice is getting warmer and it's able to more readily deform, but it still works. So in this case, the base of Pluto's ice shell is around 235 Kelvin. So that's marginally subsolidus. It's close to melting, but it's not there yet. But if I give Pluto an ocean, if the base of Pluto's ice shell is greater than 273 Kelvin, the presence of an ocean, which is a liquid, and relatively warm ice above it means that this doesn't work anymore. Why? Because the ice shell is too weak. So remember that initial, when I was stepping through before, the initial 0.5 hours when Pluto and Charon collide, and Charon is able to partially penetrate Pluto, but not completely merge because Pluto is able to resist deformation. Well, if it's too warm, it can't resist that deformation, and you produce a massive contact binary, which is not what we have. So that's certainly not what happened. It'd be interesting if that's what happened. But what this means is if Pluto had a hot start and had an ocean prior to the collision, which then thins and weakens the ice shell, that makes kiss and capture really hard. So I had a little bit of a mental breakdown about this because we've all agreed that a hot start is necessary to sustain an ocean on Pluto. And we probably have an ocean on Pluto today because it would be cool if we did. And because of the extensional tectonics. But the thing is, if Pluto's ice shell is even marginally subsolidus, which I showed you, that middle figure, if Pluto's ice shell is even marginally subsolidus, kiss and capture is still feasible. So, okay, here's where the pitch comes in. This is my pitch. what this also implies is that for kiss and capture to operate, Pluto would need a cold start to have captured Charon. So Pluto and Charon start relatively cold, but here's the thing. The actual process of kiss and capture adds heat to the system. So this is how we fix the problem. Pluto and Charon experience additional heating both during and after impact. And that could enable the ice shell in both bodies to transition from being marginally subsolidus to partially molten. So what I'm showing you here on the left is a snapshot at close to the end of my simulations of the temperature inside both bodies. And it's on a logarithmic scale, so it may be hard to tell. But the majority of Pluto's ice shell is relatively warm. And you don't have to believe me because I've also plotted the temperature on the right. So in yellow is the average temperature at Pluto's, the average temperature change at Pluto's core mantle boundary. And green is the average temperature change at inside Charon's core. And then red is the average temperature change inside Pluto's core. Nothing happens inside Pluto's core, but that's fine because it's not really involved in the impact. What was involved in the impact was almost all of Charon from the video and Pluto's ice shell. And what we found is the average temperature change in Pluto's ice shell is around 80 Kelvin, which you may think that's nothing. But this is ice, so that's not nothing. If you start with a 200 Kelvin basal temperature and you raise it by 80 degrees, you have now melted the base of the ice shell. So it's just that easy. Kiss and capture gives you the ocean that you didn't have in the cold start scenario. The other thing I will say about this is what we can't track in our simulations is the additional heating that occurs as Pluto and Charon slowly migrate outward from tides. So what I've argued here is Pluto and Charon can form relatively later in solar system history and have a cold start, and you can still produce a Pluto that has much more heat and has an ocean after capture because of the heat imparted by impact, as well as the heat that's subsequently imparted by tidal heating as Pluto and Charon evolve from this point after my simulations end. So we fixed it. And if you're wondering, what is the temperature actually doing? I did throw in a video. I threw in the wrong video. That's incredible. Oh, never mind. This is my own fault. That's a regridded version of the video, which averages out the temperatures to the point that you can't see anything, but they do look really trippy. So I can send that to you later if you just want a neat video to look at. The summary of the video is that you end up with a steadily warming core inside Charon and bulk increased temperatures inside Pluto and Charon's ice shells. So this is me trying to back up the plot that I'm showing you here on the right. No. Okay. Back to my last point, which is I said earlier that kiss and capture can reproduce Pluto and Charon at a variety of impact angles, velocities, and sizes. It sure can. Kiss and capture can also, we found, feasibly reproduce the smaller Orcus and Vanth system. Has anybody heard of Orcus and Vanth before? Yes, amazing. Thank you to my 2 Orcus and Vanth fans. Yeah, we're real Kuiper Belt understanders. So what you need to know about Orcus and Vanth is that they're really neat. They're similar in mass to Pluto and Charon. So the mass ratio of Orcus to Vanth is similar to Charon to Pluto. Sorry, is similar to Pluto to Charon. What that means is they're like Pluto and Charon, but 40% the size. So it's so simple to test whether this works at smaller sizes. You just scale the model down. And here comes Vanth, the 2 bodies. Again, you have kiss and capture, you generate some debris, but again, you end up with an intact, massive satellite around a primary. So we can feasibly reproduce Orcus and Vanth through the same mechanism. What I will say about this is that at the size of Orcus and Vanth, which are 40% the size of Pluto and Charon, sorry, 40% the mass, I should say, it is highly likely that both bodies have a lot of porosity in the outer portions of their ice shells. If true, I can't simulate that in these models, but that's the subject of future work. So this is a direct comparison. On the left are Pluto and Charon, and on the right are Orcus and Vanth, which are 40% the mass. As you can see, we can do it. I also can reproduce Arison dysnomia, but I just don't have any slides for that. So the key points that I would like to leave you with are three. First, what we found is that in the Kuiper belt, where velocities are slow and sizes are relatively small, that material strength drastically changes how Kuiper belt objects capture satellites. So it doesn't just change what happens during impact, though clearly it does, but also the impact angles, the initial conditions during which this can occur. So everything is a little bit different now. But the end result, which is capture of a massive satellite, still happens. And in the case of kiss and capture for Pluto and Charon, the main things that are worth noting is that it keeps Pluto and Charon largely intact. And it releases a satellite on this close, low eccentricity orbit that then stabilizes and migrates outwards. These changes, which are changes to the mechanics of how impact-driven satellite capture works, have potential geologic implications for the evolution of Pluto, Charon, and other large mass Kuiper belt object binaries. And what I'm getting at there is these potential relationships between Pluto and Charon's initial formation and their thermal properties and their interior structures, and how they change and don't change as a result of the impact. They are structurally largely the same before and after impact, but thermally, they may change just enough to drive an initially cold system to a system that is much warmer and might be able to sustain an ocean over geologically relevant times. And if you want to know more about this, I published a paper on it that you could read if you would like. I can also send you a PDF of this paper. And that's all I have. So happy to take any questions.
Okay, any questions for Adeene?
Thank you. That was great work.
Thanks.
This will be sort of an ill-formed question, but it goes to timing, asking when this happened and how things settled down. The one thing that I was thinking while watching this is that there is this weird little patch to the west of Sputnik Planitia of what really looks like ancient terrain on Pluto left over from intense bombardment. And I don't know when that would have happened, but it seems to me that your timing has to be such that you did what you did and everything had to be settled down and the surface had to be set up to be able to preserve a record of what happened later on. So if you can find a question in there that goes to when did it time and does that work out?
Yes. So I think a question that you could ask is, relative to the oldest geologic features on Pluto's surface, how much of a gap is there between when Pluto captures Charon and when it forms the large geologic features that we can observe? Really hard to say. Two things I can say are, first, Sputnik Planitia, being old and degraded and a massive impact basin, is thought to be the second oldest feature on Pluto. The oldest feature on Pluto, for folks that do not know, is not Sputnik Planitia, but an ancient ridge trough system that runs relatively north-south. It can be difficult to see in most images because it's extremely degraded and because Sputnik Planitia overprints it. So you can see it on either end of Sputnik Planitia. That would be the first geologic thing that happens after this giant impact. So the other thing I can say that relates to this is the collision, even though it doesn't disrupt the interiors of either body particularly much, does completely resurface. So it's effectively a geologic reset for the surface, which is, as you say, you're essentially, again, starting from zero and then accumulating all the geology that we have today. So you could say that at some point after impact, as the system starts to re-equilibrate and thermally evolve, the first thing that happens is you experience expansion and you create that massive ridge trough system. So I genuinely cannot say, because we cannot date the surface of Pluto, how much time passes, but some amount of time passes and then you start with the ridge trough system and then Sputnik Planitia forms. So the weird thing about Sputnik Planitia then is that it implies that Pluto gets hit twice by really big objects. Is that realistic? Kind of tough from a the Kuiper Belt object is really big and it's difficult to have large objects hit each other perspective, but the geologic evidence suggests that Pluto did just get hit twice. I hope that kind of addresses.
As part of this, I guess how I might refine the question is, I thought that the expansion ridge part that you referred to took a while to happen, whereas that period, that little patch of intense bombardment, I would have thought was something left over from very early.
Ah, okay. So are you insinuating that perhaps that patch of intense bombardment could be accumulation of impacts from, say, like the debris disk that forms around Pluto and Charon that then?
No, I guess I would have thought.
Or is it like preserved from before the ridge trough system, maybe?
Yes. In other words, it's really impressive. It's a small area, but it's extremely densely cratered, and it's the only part left over. So I thought that is a general remnant of the intense bombardment that happened throughout the solar system. So your event would have to happen before that, since you reset the surface.
Yeah. Yes, I would have to look at that specific area to comment further, but yes.
Some of the other known binaries in the Kuiper Belt, the primary is decidedly non-spherical. Can you explain that, or what does that imply based on this mechanism?
Well, in some cases, like Haumea, the primary is non-spherical because of its rapid spin rate. So in some cases, the rapid spin rate, it's been suggested to be a result of potentially impact, or alternatively, Haumea is spinning relatively rapidly and then loses some of its material to debris, and then you get the moons. In the case of the impact, you can get some, if you're thinking of like impact-induced reshaping to specifically reshape Pluto to be non-spherical, it's possible in a colder, stronger body where you preserve, if you're carving out some of Pluto during the impact, if you can preserve that over time if the body is relatively cold and strong. But the other option is just that the impact can just induce a high spin rate that then causes the body to reshape itself because it's spinning so rapidly in the case of something like Haumea.
And would that imply a hot start?
What? Would that imply a hot start? We don't know enough about those bodies to say. I would like to have a look at Haumea in more detail. The problem with Haumea is that it's such a complex system, because you don't just have Haumea, which is shaped like a loaf of French bread. Well, not like French bread, but the one that's slightly rounder and thicker than French bread, which has its own name that I don't know. But then it has two moons, and then the possible ring, and then the collisional family. So to address all of those things requires a lot more in-depth work. So I can't comment on that system specifically. But yeah, the thermal properties of the system are definitely going to be important when thinking about how all of that aligns. I wish I could comment further.
Maybe actually I have a couple questions.
Sure.
So one might be faster. And so on the slide where you showed off the temperature change as a function of time, for Pluto's core mantle boundary, the temperatures continued to increase through the end of the simulation. What was going on there?
Heating from tidal friction.
Okay, that was the fast one. So then the other one might be a bit more of an ill-formed question, but at the beginning of the presentation, there are all these wonderful images of Kuiper Belt binaries. The slide here talks about extension to other large mass KBO binaries.
Yeah.
Are the ones that you showed off early on, how many of those meet the criteria of being large mass KBO binaries? And are there enough statistics, and have you done enough simulations to start to kind of match? Do the outcomes of my simulations occur frequently enough to explain the KBO binaries?
Okay, so multi-part question. I'm going to try to keep track of the parts. So how many of those qualify as large mass fraction satellites? I made the decision, as did my co-authors, that all of the bodies that we showed you on that slide have large mass fraction satellites. So you may argue that something like Eris and Dysnomia, where Dysnomia is like 1% the mass of Eris, is not particularly large mass fraction satellite, but it is still much larger in comparison to Eris than the satellites of Mars to Mars and Same with the giant planets. So it's more comparable to the Earth and the Moon than it is to any of the other moons that we see elsewhere. So we are arguing that on the small end, you have the mass ratio of Eris to Dysnomia. On the large end, you have the mass ratio of Pluto to Charon and Orcus to Vanth. And within that framework, we've found that we can produce bodies that are much larger, that have a much more comparable mass, which is a Pluto and Charon scenario. We can reproduce those. And I can also, as I slowly decrease the mass fraction of the impactor, we can still produce something similar to Eris and Dysnomia. So that is preliminary work of a much larger idea. I'm hoping to submit a proposal to more systematically study the other Kuiper belt objects to see how reproducible this is and if this works for all of them. So that's something that I'm working on. So the initial work that I've shown you here, it works as you scale down in size, and it seems to also work as you also start tweaking the mass fractions. But the mass fraction piece is something that's kind of ongoing work. Does that answer your question?
Yeah, that's helpful.
Yeah, cool.
Thank you.
There seems to be a question on Zoom. If you want to unmute.
Yeah, sure. Thanks. Lots of interesting things in that nice talk. I guess I'll ask about the 4 minor satellites in the Pluto system, which are, small in mass, but notoriously difficult to explain due to the N-to-1 resonances and other things. So given that no one can explain them, I don't expect you to, but I'm just wondering your thoughts on whether those likely formed as part of the impact or something else.
I would love to be able to answer this question systematically and say we can also make those, but it's actually a difficulty in model resolution, which is always a really tough thing to tell people, but here's the problem. So the mass of Pluto and Charon are on the order of 10 to the 22, 10 to the 23 kilograms, I believe. The mass of Pluto and Charon, the smaller moons of Pluto, which are Nix, Styx, Kerberos, and Hydra, are on the order of 10 to the 15 to 10 to the 17 kilograms. So when you have that many orders of magnitude between the largest bodies in your simulation and the smallest, the problem becomes one of resolution. So I've tried to conduct these simulations at relatively high resolution, but the end result is that a single particle in my simulations is the mass of all of 4 of the other moons combined. And if you would like to help me run higher mass simulations so that I can fix this problem, please let me know. Right now I'm running 500,000 particle simulations, and I would need to run 500 billion particle simulations. So with your help, I can take over the entire HPC and we can answer this question. What I can say for real is that we produce a debris disk that, even though Pluto and Charon lose relatively small amounts of their mass, there is still enough material put into a debris disk that you could argue that you could form the smaller moons from that disk. However, as you can see, I'm doing a lot of wiggling here because the particles are bigger than the moons, so I can't really say if they're actually putting the moons in the places where they should be. All I can say is that there is material in the right general location. I wish I could give you a more satisfying answer, but that is just the result of the modeling.
Thanks.
Thank you.
This is just a simple question about methods. Is there any benefit to doing this in 3 dimensions?
This is in 3 dimensions.
Okay.
So yes, there's huge benefit to doing it in 3 dimensions. It would be difficult to do this problem in 2 dimensions.
And then I need to get a look at the time.
Another question that comes up through your talk and the question we just had over there. So, right, KBOs are quite common, 50% or more binary.
Yeah.
And you have a whole set of binaries there. And so I'm left wondering if Charon might have come in with a friend. And is that something that might have stayed bound and stick around? Is that possibly the thing that made Sputnik later on?
Maybe. So could Charon have come in with another object? Could Charon have come in as a binary already and then had another object stick around that then recollides to form Sputnik? I cannot say because I am not an orbital dynamicist, because what we know is, like I said in response to your earlier question, there is some sort of time delay in between the initial impact and the formation of Sputnik Planitia, because there's a feature in between those two, right? You form the ridge trough system first, and then after that, you overprint it with Sputnik Planitia. This implies some amount of geologically relevant time has passed. How much that is, if it's tens of thousands of years to tens of millions of years, is really difficult to say. Thus, it's really hard to comment on the survival and lifetime of an unstable binary partner.
I think we have time for maybe one more question, and then we'll go ahead and call it a talk.
I can just yell from here. Just commentary on timing of Sputnik Planitia versus Charon capture, at least with the kiss and capture method, which produces Charon at like 2 or 3 Pluto radii, and then timing in there. Not that this is proven, but it seems pretty unlikely that a Sputnik Planitia could happen while Charon is that close without majorly disturbing Charon's orbit.
This is true. So presumably Sputnik Planitia occurs after Charon has migrated outwards.
Seems like we need to figure out the tidal expansion timing.
But the tidal expansion and tracking that in more detail is the subject of future work, because that's not something that SPH can handle.
Yeah.
It's simply not built to look at the evolution of the system on geologic timescales. It's compelling though.
Okay, all right. Let's give Adeene a hand.